Okay, we're going to look at the examples from lecture 7. First of all, we're going to look at the momentum equation, and then we're going to apply it to force round a bend and apply it to a numerical example of flow, of the force that flow going around a bend causes on that bend. So, forces in moving fluids. We know that forces exert a force, e.g. Aircraft swings, we get lift, we get a jet of water. If you get hit by a jet of water, you know you've got a force. Water turns a turbine, there's a force involved there. Nozzle of a hose. Now we'll talk about a nozzle of a hose in other examples. And these are analysed using the momentum equation. The momentum equation is application of Newton's second law. Rate of change of momentum is equal to the force, or F equals ma, applied to a fluid. And this is what we're going to see in these lectures. Statement of Newton's second law of motion as applied to a fluid. So F equals ma equals rate of change of momentum. What mass do we use for a fluid? Well, let's consider the stream tube. Section 1, fluids going in at section 1 and coming out at section 2, and we've got density going in, velocity going in, area going in, and these coming out, and they've all changed. If we take a slice through that stream tube, we get the velocity times time gives us the distance that any flow going in has moved in a time delta t, and we can look at that volume and look at the momentum of that volume, and we can do some analysis. So we'll assume steady, non-uniform. Non-uniform means it is changing with space. So time delta t, we've got this much fluid moving, fluid moving that distance. Multiply it by a, we get the volume. Multiply the volume by the density, we get the mass. Mass, we'll multiply that mass by the velocity, we get the momentum. This is in terms of what's going in, so we've got the subscript 1, got the momentum going in. We can write this same expression for what's coming out. So let's write this for what's going out. Momentum leaving is very similar, we've just got the subscript 2. Now, bear in mind Newton's second law, rate of change of momentum. Well, we've got two momentums, and one going in, one coming out, and these are different, and we look at the difference in the time delta t. So as our change of momentum, it all took place in the time delta t, so the force on the fluid is equal to that. Now we can see that we can cancel our delta t's out here. I'll do that for you. We can relate velocity u1 and u2 using the continuity equation, and we can cancel the subscripts of rho, because we're assuming a constant density fluid, just single rho. And this simplifies quite quickly to that the force on the fluid is rho q times the velocity out minus the velocity in. Nice and simple equation that we can apply. This is one to remember. We can actually write this same equation in terms of rate of change of mass. Instead of rho q, we use m dot. You'll see that in some books, we're not going to use it in this lecture theatre. We're going to use this form with rho q, because we have a constant density, so this works more easily. And this force is the force on the fluid, yeah, and it's in the direction of the fluid. Force is clearly a vector, as you know, and it's in the direction of the fluid flow. Now that equation that I showed you with u2 minus u1, it needs to take into account the velocity direction. So let's look at applying it in two-dimensional case where we can take in velocity directions. I've drawn a flow around a bend here, and we've got the angle theta going in, theta 1 going in, and angle theta 2 going out. We're going to resolve our velocities into the x and y direction and look at the forces in the x and y direction. So let's say we've got fx equals rho q u2 cos 2 theta minus u1 cos 1 theta, and I'll shorten the u2 cos 2 theta to u2x. So these are equivalent, both the same. Okay, just a shorter notation. And I've indicated here in green, the red, the fx, so the velocity x, and in green in the y direction we get fy equals rho q u2 sine 2 theta u minus 1 u1 sine theta 1, and again I use this short notation for this expression here, just to simplify things. So the red lines indicate the velocity in the y direction. It's quite simple geometry resolved. Once we get our fx and fy, we can draw a vector force diagram and calculate the F resultant, that green line shown here, and that applies at an angle phi, and simply use Pythagoras and simple trigonometry to get the angle and the resultant force. So the total force on the fluid is equal to rate of change of momentum through the control volume. Now we can break down this total force. There's a summary of the equation. It's a vector acting in the direction of the fluid. I said we've got a total force, and we can break this down into a force on any solid body, e.g. a pipe, a force on the fluid body, e.g. gravity, so the weight of the fluid, and the force of the fluid by any pressure difference, pressure force, Fp. So we say that this total force, rho q u out minus u in, is equal to these three components. This is quite convenient. It's often Fr that we want to calculate, the force that the fluid is causing on the bend or any structure. Okay, so that's one thing you do need to remember. Okay. That Fr is in the direction of the fluid, the force that the structure needs to withhold is the reverse of that, or minus Fr. So here's the general picture. Force is in the direction turning the fluid. So this fluid is going round a bend. So let's see, where would you expect a force acting on the fluid? We're pushing it in that direction round the bend. Acts on the fluid, turning the fluid and squeezing the fluid. and the force of the fluid acting on the structure is that R in green, acting on the bend, pushing, trying to flatten the bend out. Hope that clarifies what forces are acting on what. The red force is acting on the fluid, the green is acting on the bend. Because the a fluid acting on a bend, a force acts on the bend, then we need to take into account this can be serious for water supply pipes. It can cause breakages of joints, particularly at very sharp bends. So here's a picture of a sharp bend, and it's encased in a concrete block. This is known as a thrust block, to take the thrust or the force due to the change in direction of the fluid, the rate of change of momentum going around that bend. Here's a picture, and we can see a thrust block there, a concrete block, just holding this pipe bend in place, and it's at that point the bend that there is a high force. Why this is a particularly high force in this bend? Because it's a very steep pipe coming down from a reservoir, and it'll have a very high velocity. So high velocity, rate of change of momentum, means a high rate of change of momentum, so a high force. Now we can work out a systematic way of solving the force on a bend. So here's a generic bend. I've aligned my coordinate system with the inflow, so got θ1 equals 0, and I'll drop my θ2 and just say theta is equal to 45 in this example. And this pipe is going upwards, and so it raises from by 1 meter as the flow comes out. So the systematic way, we draw a control volume, any volume that encompasses the inflow and outflow section. We do a coordinate direction, and as I've just said, we've chosen a coordinate direction to be most to help solve the problem most easily, most convenient, and that's usually with the x direction in the direction of the flow. Sometimes it's most convenient to have the x direction in the direction of the outflow, but let's in this case the inflow. Calculate the total force, which is our rho q u2 minus u1, and we'll do that in both the x and y direction. Calculate the pressure force, body force, total force, resultant force, and we use that equation to actually calculate one of the unknowns. So we'll calculate the other three and usually calculate the resultant force from that equation. Let's have a look at this example. 45-degree rise out of a pump. So we've got a big pump to the left hand side, and it's pumping water going upwards. The diameter changes as it goes up from 150 millimeters to 300 millimeters. Pressure at P1 is 100 kilonewtons per meter squared, or 100 kilopascals. The outlet is 1 meter higher. The volume of the bend is 0.075. Now the volume will enable us to work out a mass of fluid, the weight of fluid acting downwards. Okay, we've got a mass of fluid acting downwards due to gravity trying to pull this fluid down. Flow rate in this example is 0.3 meters cubed per second. We're going to have to work out the velocities, so we should do that at the early stage of this calculation. So find the reaction force R acting on the bend. Remember, FR acts on the fluid. So work out the areas, always convenient to work out the areas. Keep it to 3 significant figures and the calculations will be sensible then. Okay, we're going to calculate the force in the x direction. We're going to use this equation. So similar to the one we've shown before, that our theta here is now just theta and not theta 2, because we've set theta 1 to be 0 by choice of the axis. So theta equals 45 degrees. Okay, we need to work out the flow and velocity. We've got Q equals A1 U1 and A2 U2. Work out the velocities. These come out to a velocity of U1 is 16.9, so 17 meters per second. This is extremely high. It's coming out of a pump, so we could expect high velocities coming out of a pump. If you're getting anything near 10 in a pipe, you need to check it very carefully. Anyway, let's use these. We work out the total force in the x direction. Comes out to be minus 4194. So it's acting to the left on the fluid. In the y direction, y2 sine theta minus 0, because sine of 0 is 0. And this comes out to be 900, acting vertically upwards. So that makes sense. It's pushing the fluid up and to the left. Let's calculate the pressure force, and this is equal to the pressure force at 1 minus the pressure force at 2. What's pressure force? Well, pressure force equals pressure, and this is pressure, not rho, times area at 1, pressure times area at 2. And we need to resolve the areas. So at 2 we've got a theta of 45, and at 1 we've got a theta of 0, so we're going to get 1, so it's going to be P1A1 minus P2A2 cos theta. Let's apply that in the x direction. In the y direction, a similar expression. Pressure at 1 minus the pressure at 2 in the y direction, resolved in the y direction. Sine 0 is 0, so we'll get a minus P2A2 sine theta. We need to enter here P2 and P2, and we don't know those. We do know the P1, we were given that. So where do we get pressure P2 from? Well, we get that from the Bernoulli equation. Here's our Bernoulli equation. You've seen this form before. I've got an extra term on the end here. Now this is a head loss. Now if we got any friction losses, we might apply that. So we're going to ignore this because we're going to say there's no friction losses. But we now have, from in this equation, we have P1, we have U1, we have rho G, we have Z1 minus Z2. So Z2 minus Z1 equals 1 meter. And we have a U2. What we don't know is the P2, so we rearrange this and make P2 the subject, and we calculate P2. So pressure P2, put these numbers in, and we get P2 is equal to 225.3 kilonewtons per meter squared. We can then put this into our pressure force calculations. Px is minus 9495 newtons, and Py minus 11,260 newtons. So that's the force on the fluid due to the pressure difference. The body force. The body force is the weight, the force due to gravity. Always acts down, because gravity acts down. So body force is in the y direction. There'll be no body force in the x direction. So the body force is down, so it's negative rho g times the volume. We were given the volume 0.075, and that comes out to be minus 735. Remember the minus because it's down and y is positive upwards. Body force in the x direction is 0. It will always be 0 because gravity only acts down, not horizontally. So we've got these two equations for the resultant, and we're going to calculate the resultant force. The unknown here are these two expressions, Frx and Fry. We've already calculated all the other six expressions. Comes out that Frx is 5,301 and Ry is 12,900. Use a force diagram. They're both positive, so the force diagram will look like this. That's the resultant comes out to be 13,950 newtons or 13.95 kilonewtons, and the angle there 67.7 degrees. Okay, that's pretty much calculated. What we wanted to do is calculate the force on the bend, because that Fr is the force on the fluid acting like that in that direction, pushing it round 67 degrees. That looks about right. That green arrow looks about right, the force causing that fluid to bend round. R is the force on the bend. It's in the opposite direction, so that capital R there, red, is the force acting on the bend. Okay. So we've seen the momentum equation and how we've applied it to force on a bend.